Good afternoon. So today we're going to start off with reducing our fraction class so that we can make some critical assumptions about the denominator always being positive. And for example, one really nice assumption we'd love to be able to make in the interest of numerical stability is that the fraction is always in lowest terms, or most reduced form. Okay? That way, if we want to test for whether or not two fractions are equal to each other, we just compare the numerators and the denominators. So without thinking too much about how to actually do this, you know the algorithm to simplify a fraction. You find the factor, you factor it out and you cancel out the common factors. Well, there's an algorithm for that. It's very well known. Euclidean algorithm, and we don't have to actually understand what it's doing. You don't have to have a clue as to why this works or how it works. All you need to be able to do is scroll down and look at this and say, wait a minute, that looks like something I could code up. Okay, so implementations of the algorithm may be expressed, this is on the Wikipedia page, may be expressed in pseudocode. For example, the division-based version may be programmed as, okay, while b does not equal 0, well, we know how to code that up. T equals b equals a mod b, a equals t, return a. Okay, so there's just a while loop. Okay. Now, what about, the only real slowdown in this algorithm is the mod operation. But you know how to do mod, right, in C++? Just the percent sign. All right, so this is straightforward. What about this one here? Well, that's even easier to parse, right? I mean, that's almost literally C++ code. You make that not, exclamation equal, you get rid of those colons, and you almost literally have C++ code. Okay? So, again, the emphasis here is not on, can you figure this out, or modify this algorithm to do, no, don't even bother with any of that. Assume all of the hard math has already been worked out, it's communicated in a certain form, and all we're tasked with doing is just translating it into production quality code. Okay, so let's just take this here. Let's see. Here we go. Here's something very important. Contrary to the division-based version, which works with arbitrary integers as input, the subtraction-based version supposes that the input consists of positive integers and stops when a equals b. Okay, so this one assumes a and b are both positive. Okay? Whereas this one should be a little bit more robust to positive and negative numbers. Okay, so let's try this. Let's make a function. We'll call it GCD. Okay, and we'll just make it an int, GCD, int a, int b. Let's see. Okay, notice how it copied over the funny not equals symbol, but that's not proper code. Okay, while b does not equal 0. Let's see. So we're going to have to create a variable t. Let's just set it equal to 0. Okay, and let's just do t. And I replace mod with %. Throw in some semicolons. I wonder if this will work. Let's see. Semicolon. Of course. Okay. Now, here's one thing to keep in mind. Should I pass in a and b by value, by reference, or by const reference? So the parameters a and b. Here I've chosen to pass them in by value. Should I modify that decision? What do you think? I have a no. Here's a kind of rule of thumb. Maybe you learned this in 10A, maybe you didn't. I always pass fundamental types like int, size t, double, by value. Unless I specifically need to access the actual value and modify a variable that's inside the function. But if it's the choice between a pass by value or pass by const reference, always pass by value. The overhead involved in making a copy of an int or a double is not worth the overhead. In fact, you may even get more optimizations by passing by value rather than by const reference. There are very weird reasons for why that might be the case. Okay? But in general, if it's a fundamental type, you don't pass by const int reference or const double reference. Just pass it in by value. Now, you may want to pass in by int reference. You might want to pass in an int reference. That's fine. But always err on the side of passing by value, because the overhead in making the copy is really not... it's typically better to pass in by copying the int or the double than it is to do a const double reference. Okay? Throwing in a const double reference throws in a lot more constraints on what the compiler can do with the code. Okay? So that's that. Now, here's the better question. Should I pass these in by reference or by value then? How about A? Reference or by value? How many people say by reference? How about by value? Whoa, why so strongly feeling about value? Yes, there is an answer to this question. Well, I'm returning A, but I'm returning it by value, right? What am I doing to A inside the function is the better question. I'm changing it, right? So if I want to pass in, numerator comma denominator to this GCD function, I probably don't want to change the actual values of numerator and denominator, okay? So this pseudocode that we got from Wikipedia assumes A and B are some values that we can overwrite, okay? And so similarly here, we're going to pass in A by value because we're going to overwrite its current value. We're going to modify that value of A, and the modifications to A are eventually what's going to get returned. Okay? Now with B, what about B? Same thing, right? Pass by value. Because look, you're overwriting the current value of B with something else. You're overwriting the current value of A with something else. If you don't want someone to accidentally if you don't want someone to accidentally call this GCD function and all of a sudden their variables get overwritten, you don't have a choice. You pass everything in by value. And that's fine. We're only working with int values here, so it's not a big deal. Okay, so we have this GCD function. We should comment it, just like that function above it. Calculates the greatest common divisor of, I guess, integers A and B. It's supposed to work for all A and B, positive or negative, just not 0. If it's 0, then there's no telling what this is. Well, I mean, we could figure it out, but it's not guaranteed to work when there's a 0. Okay. At param A is, I don't know, just one of the values. It's symmetric in A and B, so B is the second value. I don't think they have an actual significance. But it returns the GCD of A comma B. And that's pretty much how to describe it. In math terminology, that is how you would write it, GCD of AB. Okay? So let's see if this actually works. Okay, GCD algorithm. So let's do int. Let's call it division factor equals GCD of numerator, denominator. And then once we get this division factor, what are we going to do with it? So for example, if we have, let's do 15 divided by 5, division factor is going to equal what? 5. Okay, so what do we do with that 5? Yeah, now divide numerator and denominator by division factor. Okay, so numerator divided by equals division factor and denominator. Okay, let's just print out numerator and denominator just to be sure. Just to be sure that this worked. Okay, so Build succeeded. Okay, let's call this reduce function. Did I make it? I made it private, I think. Let's change it. Let's make it public for now. Yeah, let's make it public for now so we can call it and just check to make sure that we did it right. In fact, let's take out the print statement and we'll just call print after we call that function. Okay, so that's the beauty of this is the beauty of having a print function, is that you should not have couts and cins or whatever inside of your functions. You just do the calculation inside the function and then you call a print afterwards. Okay? Or if you do cout something inside the function, it's merely for debugging purposes. Eventually you're going to take all those out. I saw several students' attempts at homework where they had to add and subtract various polynomials. They didn't actually do the addition or the subtraction. They did, but they stored it in a copy and they just printed out the updated version. And like, no, I wanted those functions to actually perform the arithmetic, and then you print out the function. That way you don't have to think about, how do I print it out in this function? Or how do I do it in this function? Completely modularized, you do one piece at a time. Okay, so let's go to main. All right, here we go. Let's get rid of this stuff. Okay, we'll keep this fraction A, B stuff. All right, now we're going to do let's do a b dot print. Let's call b dot reduce, and let's do b dot print. Oh, let me put in. There we go. Look at that. Okay, and it reduced it for us. Let's see if it can handle negative numbers. Okay, well, it did that. That's not very nice. But where did the negative? How did the negative sign get into the denominator? I thought we took care of that in our first part, last class. How would the denominator creep back in to the negative? Yeah, because the GCD probably returned a negative greatest common divisor, right? So kind of makes you stop and question maybe the order in which you perform those operations. Okay, so let's just switch the order. Okay, so in our GCD, in our reduce function, let's calculate the GCD first. Okay, and then we'll take care of the minus sign. Let's see if that works. Ah, look at that. Okay? This is how you, again, am I doing anything that intelligent? No. I'm really not. Okay? I'm just arranging intelligent pieces somewhat more intelligently than just throwing them one after the other after the other. Okay? So that's where the logical thinking comes in. It's not about math. It's not about anything that complicated. It's about understanding how the pieces can fit together in a way that's very elegant. Okay? So that's that. Let's test to make sure that that wasn't just a fluke. Oh, I'm almost there. Let's throw in a bunch of negatives top and bottom. Yeah, look at that. Got rid of both of them. Nice. Okay. And then let's try throwing in one that doesn't reduce, one that is already in lowest terms. Cool. And it got rid of all the minus signs. Okay. So we're in good shape. Now let's see, though. Okay. Fraction b of. What happens if we try to do like 5 of 0, comma 0? What do you think's going to happen? So first of all, it compiles, right? And it's going to run. It's going to run just fine for the first part. Because there's nothing inherently incorrect about having a denominator variable that's an int equal to 0. But it's how we use it, how we interpret it. That's where we can cause some significant damage. So let's just see what happens. Oh, look at that. What did that do for us? In a sense, it standardized all of the potentially bad fractions we could have which divide by 0, right? If we have 5 divided by 0, that's a bad fraction. We might be given that initially. We might want to cause an error to occur. But we may want to reduce whatever fraction we get input initially, and then we can test, instead of testing for A positive or A not 0 and B 0, we can just test for B 0 and A 1, because it's always going to get simplified to 1 over 0. Okay? I mean, just to kind of demonstrate that again, let's do negative whatever. Okay? Gets reduced to 1 over 0. Okay? So no matter what the user inputs in so far, it gets reduced to some standardized, version that we can there easily test for. Okay, what is the baddest fraction of all? 0 over 0. I'm scared to think about it. Okay, let's see. See what we get. Okay, you guys ready? Ready for this? All right. Obviously, it compiles because it's a value thing. Okay, but let's see what happens. What? Whoa. Okay, so in other words, bad stuff happens. Okay? Now, in this class, we're not going to think too hard about this case. Okay? In 10C, I will, I guess, permitting on time and what topics to go over, there are very nice ways of doing error handling. Checking for a case like this, recovering from a case like this, things like that. Just keep in the back of your mind the idea of, hey, wait a minute. Should there ever be a fraction that's 0 over 0? That should be interpreted as a fraction? No. So this behavior is probably, not stupid, but the fact that it would crash when there's a 0 divided by 0 is actually fine, right? Because you would never have a 0 over 0 anyway. And if you did, you would probably want it to crash to let you know you're doing something radically evil. Okay? All right? Or maybe you have a different perspective on the matter. But the point is that 0 over 0 did not simplify to 5 over 2. That would be really bad. Okay? Having a fraction which doesn't make sense cause the program to crash is not the worst type of thing that you could think of. Okay? So let's forget about that case, and let's just assume it's never going to happen. Because the only way it really should be able to happen is if you construct a fraction with a 0 over 0. Okay? So again, in 10C, we would handle this case, and we do it all the different versions, but let's just for now assume we're going to be nice about it. What if we did a numerator of 0 over something? What should we get? And 0 over 1 is what we would want. And that's what we get. How nice is this? It's kind of nice. Okay? Let's put it in. All right, so let's now get rid of reduce as a public function. We don't want the user or the programmer to ever call the reduce function. We want reduce just slowly, just kind of silently working in the background. And anytime we change the values of numerator and denominator in some way, we're going to call the reduce function. Okay? And that way, no matter what numerical operations you perform, at the end, what does it do? Reduces it, and you don't have to worry about it. Okay? So if you want that manual control, sure, leave it as a public function and leave the fractions in those weird forms. But if you want a fraction type that always reduces to lowest terms, well, it's actually not that difficult to do. Well, let me leave it in there first. Okay? So I'm going to change reduce from public to private. And then we can see exactly what that does. Okay? Now we get an error which says fraction reduce cannot access private member. So we get rid of this. And now the question remains, which member functions or which functions in general should we call the reduce function in? How about the constructors? Default constructor, what about that one? No, because we're going to default initialize that to something like 0 over 1 or something like that. So we have complete control over that value. But what about the fraction with one parameter, just the input numerator? No, right? I mean, it's going to be numerator divided by 1. You can't, I mean, that's already simplified. What about the third one? Yes, okay, so all right, so we're going to put it, let's just do it right now. Okay, so we'll put it in there, and we'll come back and take a look at our list. And let's see what this does. We have it, let's see. Here it is. Here's our function. It looks pretty empty, right? Because we field initializer listed, wait, I don't know how to use that as a verb. We use the field initializer list to initialize all of our member variables. And then what code am I going to write in here? Reduce. Okay. Well, let's see if that worked. Okay, so let's start with, let's go back to our good old fraction b. Fraction b of 3 comma 6. We'll just do one of those prints. Okay, are you ready? Are you excited? All right, let's see what this does. What should this print out? 1/2, does it? Oh, yeah. Okay, that's kind of cool. I mean, you know, we did that. Literally, I mean, go back and watch the video. We started from scratch. You can watch every single bit of code from number include IOStream until this very moment. Every single bit of code is completely just one piece at a time. And now we get this magical fraction class that reduces itself. Okay? So that's the first step to do it, okay, the constructor. Now, what other functions are going to be caught? So for example, here if we do, you know, b plus equals a, now we're going to end up with 4 over 4, right? Okay, so we start with 1/2, we end up with 4 over 4. So which functions now, let's see, do we need to call the, well, this one I took away. Reduce on. Plus equals, times equals, all of them? Okay, so what do we know about operator plus and operator times? They call plus equals. They call times equals. So I only need to put reduce in which functions? The plus equals and the times equals. Now, any function I make that uses those functions gets the reduce functionality itself. Okay? In other words, you don't have to write reduce everywhere. Okay? You put it in a few key places, the only places where the code can actually modify the variables, and then it only gets called once, and it only appears where it needs to appear. Okay? This is the idea. It's not about actually making a fraction class. It's about making it in a way that is efficient, easy to follow, and easy to extend. Okay, let's do it. Operator plus equals. So we do a bunch of stuff here, and then what do we call at the end here? Reduce. And make sure you call reduce before the return statement, of course. Here again, reduce. Now what about operator plus plus? Why yes, why no? But does it call plus equals function? It doesn't call any other function. What does it do? It adds the denominator to the numerator. Can we come up with any examples where, after doing that, the fraction would not be in lowest terms? Think about that one. Okay? Think about that one. Now, let me ask you a question. If you didn't want to think about that one, what would you do? Just put it in. If you want to be safe, put it in and do the following. Reduce. Maybe we don't need this. We shall ask a number theorist. All right, or just think a little bit harder about it, okay? And try to come up with if you can come up with one example, right, where it wouldn't simplify automatically, where you need to call reduce, then you need to call reduce, okay? To be safe, you can just call reduce, and you don't lose any sleep over it, okay? Throw in the note, move on, okay? Technically, it's correct. It may not be as optimal as possibly imaginable, but none of the code you write will be anyway, so it doesn't matter, okay? Well, it doesn't matter at this stage. Now, how about postfix operator plus plus? No, right? Because you're not actually modifying numerator or denominator directly. You're just calling the prefix operator plus plus, and that one's got the reduce built in anyway, so you're good to go. How about operator plus or operator times? Nope, because they're actually calling, they're not calling or modifying numerator or denominator, they're calling a function on the fraction objects themselves, and those operator plus equals and times equals call the reduce function at the end. Okay? So unlike the plus plus, where you're modifying the numerator and the denominator directly, these ones don't actually modify the private member variables directly. They merely call other member functions. How about this negation? Okay, this is a good one. I like this one. This one's simple though. Let's reason it out. Okay, what assumption can we make before we even go into this negation function? What assumption can we make about any potential minus sign in the fraction? It'd be in the numerator, right? The numerator would be negative. The denominator wouldn't be negative. So if we throw in a negative to the numerator, well, then if the numerator was positive, then the numerator becomes negative. And that's fine, because we always want the negative to be in the numerator. And if the numerator was negative, and we throw it in, that would make the numerator positive. But that's positive over positive. So it's fine. Do you need to call reduce? No. In particular, let's write it in that we don't need to call reduce. Okay, let's put it in the comments. To say, basically, this operation preserves reduced form. No need to call reduce. Okay? And again, I should have comments there. All right, now, now we come back to it. Okay? Let's run this code first before we look at operator less than and equal. Okay? So here we go. Oops. So we showed before when we added 1/2 and 3/6, we didn't get 1 over 1. We didn't get a 1. We got a 4 over 4. But now we've thrown in reduce to the plus equals, the times equals, all that jazz. What happens? Yes. Okay? There's our reduced fraction. Okay? Now let's do something fun. Let's do like blah, 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 and blah. Now, should that be in reduced form? Yeah. Don't ask me if it is to verify that. It should be. According to everything we've done, it should be. Okay? So there you go. Now you can hand this code off to your little sibling and be like, hey, do you need help practicing reducing fractions and checking your answer? And there you go. Okay? So I tried to get my niece to do programming, but it didn't go so well. But I mean, this is just to give you an idea of, okay, if you can conceptualize it, eventually you can put it in a framework where you can actually get the operators in the code to actually look like it should. Okay? So that's good. Now we go to the operator less than. Now remember, what was less than ideal about okay, we wrote this code a while ago. Not too long ago. But we wrote this code basically not today. here's the question. A, can we read the code today? That's very important. And B, can we, now that we've added an additional assumption that the fraction's always going to be in reduced form, can we add or modify this code to make it better? Okay? Usually if you add more restrictions on the possible values, you might be able to make other functions work better. Okay? There's less things that could go wrong. So what did we do for this operator less than? Yeah, in the back.
We turned the numerator into a double, and we divided it by the denominator and compared it to the other one.
Yeah, so we basically converted the fraction into a double type. Okay? We said, okay, well, I want this fraction to be interpreted in the computer as if I had written, numerator divided by denominator, and I put in like a decimal point when I wrote it, just to make sure it's double arithmetic. And then I'll compare those two double values. Now, what is the only thing that's kind of not so ideal about this? It's not the only thing, but what's the main thing that's really not ideal about this? Accuracy. There might be an instance. Remember that really gigantic fraction that appeared on the screen just now? Maybe I'm comparing that fraction to another fraction, and the denominator is maybe one more than that denominator, and they have the same numerator. Those are going to be pretty similar as a double. As integers, we know that they're exactly, we can determine that they're exactly different, okay? But when we convert it to double, we might lose that extra bit of precision, which states that while they're close, they are definitely not exactly equal, okay? So now that we've assumed that all of our fractions are in the lowest reduced form, if I wanted to test for whether or not one fraction was strictly less than another fraction, what could I do? Now I can cross multiply, but, why can I cross multiply? Yeah, because now I've guaranteed the denominator is always positive. So, now that I've guaranteed that the denominator is always positive, I can cross multiply the denominators at will. I couldn't do that before. Okay, that was the one thing holding me back, is there was a chance that I was going to have a negative in my denominator. But under my new assumption now I can do the cross multiplication. Again, it's not extremely ideal, because you might still do some numerical overflow in that multiplication. But as a first step beyond this numerically bad version, or numerically kind of not so ideal version, we can maintain a very precise level of accuracy. So let's, first approach, convert to doubles. Second approach, assume denominators are always positive. Now we can cross multiply. So we're going to do a times d less than b times c. Okay, so now what we do is we do int. Actually, I should do int reference a equals. Can I do that? No, I have to have a constant in front. That's fine though. Well, let me just write int a. It's fine. Okay, int a equals left-hand side dot numerator. Int b equals, I think I did this before, right? I wrote this code somewhere else. Yeah, I did this. I should really functionalize that somehow. Okay. So we do left-hand side dot. Okay. And now we do a times d less than b times c. Okay. That sounds good in theory. Okay. Now the only thing that of course could go wrong is that you could have numerical overflow here or numerical overflow there. Okay? That's where things could go wrong. But one safeguard against that is that because we're always in reduced form, rather than potentially have a really huge numerator over a really huge denominator, a lot of those cases are going to get simplified out to smaller values. Okay, so it's a little bit better, but it's still not perfect. What you would really want to do is look at all the different cases of values of a, b, c, and d. So for example, if both denominators were the same, how would you tell if two fractions were less, one was less than the other? Compare the numerators. Now, if the denominators are not equal, then you have a little bit more cases to think about. Okay, but as a second round, I think that's good enough. Okay? Most importantly, there is no numerical imprecision as long as your values stay within what's capable of ints. Okay? Doubles are notoriously not 100% accurate, but integer arithmetic, as long as you stay within the bounds, is going to give you an exact answer. Okay? So that's what's sort of important in the back of my head is, okay, for most examples, this is going to give me an exact result. And if I need to go beyond that, then I'll think harder. Let's do the same thing with operator equal equal. Well, for the first approach, what did we do? Our first approach was to do what? Cross multiply. Okay? Again, if we know that all fractions are in reduced form, then what do we get to do? Just compare them directly. Compare numerators, compare denominators. Okay? Second approach, assume fractions are in reduced form. Compare numerators and denominators directly. Okay, so let me put this up here and comment it out. And then instead I return, well, let me copy and paste this line back. Okay. Numerator, and we'll write equals equals left-hand side dot denominator, and then we'll do and right-hand side dot numerator. Oops, wrong direction. Wait, I did something wrong, didn't I? Yeah, I need to swap these guys. Denominator, denominator, numerator, numerator. All right, there we go. Okay, does that make sense? Oops, does that work? Okay. Okay, how about operator not equals? The same thing, yeah. Okay. See how much? See, there's really not that much you need to do, and this is the point with homeworks 2 and 3. With homework 1, with your polynomial class, you already defined plus equals, times equals, you have your print function. Homework 2, you're not really, I don't think you're writing any real difficult code for polynomial. All you're doing is creating the logical structure of the input-output operators, or the logical structure for the operators' functions. And then for homework 3, that's literally all you're doing. I don't think you're actually doing anything other than that. Okay? And in fact, the rational class is so easy, you could probably just watch the lectures again and know how to do it. Think about it. Okay, so here we go. Let's keep going down. Okay, we're back to GCD. We're back to reduce. And that's everything. That's all the operations. Okay? So in our main now, we've got access to pretty much most of the same operations that we would want. Of course, I didn't do minus equals or divided by equals, but as a good exercise, you may want to implement those yourself. Okay? Just to make sure you understand how it works, how the input-output process works. Okay. Are there any questions on this style? Okay, another thing you can do, let me just do it right now. You know how you have an operator minus? Well, there's actually an operator plus. Unary operator. It's just like minus, right? If I write minus 5, that's negative 5. If I wrote plus 5, what would that mean? Just 5. Now, that's math. Forget about math. Okay. If I have a variable, and I write, say, fraction, let me write it, actually. Okay, here we go. So if I have a fraction, say b, those are large values. fraction b. Now, if I wanted to write fraction c equals negative b, what does this mean? What is the C++ code doing? First, it does what? Just for this fraction c equals minus b. What does it do first? It's going to create c actually last. Okay, so forget about that. Just focus on the negative b part. What does the negative b syntax get converted into? Yeah, okay, so what does that function return? So it's going to call this function I mentioned up here. Okay, so mathematically it's going to return the negative of the fraction. But programmatically, or C++, what is the return type of operator minus? A fraction value. Okay? You don't take the current object b and just minusify it, okay, or just minus it. You take b, you make a copy, and you put a minus sign in the numerator. So you're going to return a copy of a fraction, but with a negative in the numerator. Okay? So a completely new fraction object, and then fraction c is going to assume the value of that new fraction object. Okay? But in particular, if I were to call something like, here, this is where I'm trying to get at here. If I do fraction versus, what is the difference between the, hang on. What is the difference between these two lines of code? Okay? So say b is, let's just say b is 1/2. Okay? What is fraction c going to be? 1/2. And then after that line, what is b going to be? 3/2. Okay? It gets incremented by 1. Now, with fraction d, what is fraction d going to be? Minus 3/2. Very good. Yeah, okay. Minus 3/2, because it takes the value of b, minuses it, returns that value, a new object with that value of minus 3/2. And then what does it do? It calls the postfix ++. What does the postfix ++ do? It makes a copy. It returns the value of minus b, right, before the increment. And then what does it actually increment? Does it increment b? It increments the copy of b that was made, that was returned by the negative b function. Okay? You might have to go back to the video a couple times and listen to what I said if you didn't catch it right away. Okay? So let me just reiterate that in code. Okay? So what this does, we all know. This one, okay, returns the pre-incremented value of b in the form of a copy. B gets incremented. Okay? To 3/2. Okay? Now, when this line gets called, minus b returns what? Yeah, a copy. An object with value minus 3/2. And then what gets incremented? The copy gets incremented. Okay? So at the end of this line, now b is going to be what? Three-halves. Okay? Because the negative b says take the current value of b, return a copy with the negative value, and then the postfix gets applied to that copy, and the original variable b is nowhere in sight. Okay? This is the logical, this is what has to be understood. This is what makes it different than mathematics. Okay? So now if I try to type b dot, if I did b dot print, it should be 3/2. And it is, thankfully. Why is it? Oh, I'm doing it there too. Okay. Okay, so that's 3/2. That's the explanation. So, if I ever wanted to convert, this is the key now. Let's suppose I wanted to convert a variable a fraction variable a, into a copy of itself. I don't want to pass the variable a into a function or use the variable a. I want to make sure that I make a copy of a and then apply whatever operation to that copy. Maybe I will overload the operator plus to just return a copy with the same values. Okay? Just like negative returns a copy with a different value, just a negative thrown in, we can overload operator plus to literally just return the exact same value, but in the form of a copy of that object. So let's go minus. Okay. Operator plus, this is going to get called using plus p. Okay, something like that. So we have fraction p, and we do plus p. This returns a copy of the value of p exactly. Okay, and in fact, we should, rather than doing this, we should just do star this. We're going to make a copy, and we're just going to literally return the copy. Okay? Does it kind of make sense? Okay. So does this really do anything? I mean, yes and no, right? I mean, it gives you the ability to very quickly grab a copy. All right? This is also why, if you try to do, remember I did this like int okay, watch this. Remember if I did like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember I did that? Oops, IA. And I was like, haha, see, this works. Isn't that cool? But then I said, oh, but if you have an odd numbered one, odd number of pluses, it doesn't work. Why doesn't it work? Because what does this return? A copy. Okay? Then you can't increment the copy. You can only increment if it's an int. You can only increment the actual variable itself. Okay? So by creating an operator plus that returns a copy with the same value, we are, again, mimicking the behavior for ints. Okay? So again, we didn't do anything mathematically, but we did something in the sense of programming-wise with operator overloading. Okay? Wednesday, we will go over overloading the subscript operator. Okay? In other words, you could do this. You wouldn't do this for a fraction object, but you could. You could overload it. You could do something like a of numerator and you could write code to make that compile and run and actually just print out the numerator that's contained in a. You could also write something like a of 0 and say, oh, I want a of 0 to give me the numerator, a of 1 to give me the denominator, and then a of 7 to give me, I don't know, 0 or something. Okay? Now, you'd probably not do that, but you can do this. And if you create a class, I don't know, if you created a class like maybe a polynomial class which contains a vector of coefficients, and you wanted to, I don't know, maybe access those coefficients directly, you might want to overload these square brackets. Or parentheses. You can overload parentheses as well. Okay, so we'll do all that starting on Wednesday.